Hi, I'm at Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Andy Nightingale of Arteris. We're going to talk today about cache coherency in heterogeneous systems. Andy, what's changing in cache coherency today, and what's different now versus what it was in the past?
Cache coherency really has been with us for a long time now. It started off as software coherency, and then it's moved into being supported by hardware. So traditionally, the point of coherence in the SOC has been in the DRAM, and that's been fine, right? But what's happened recently, or what's happened over the last few years, is as single-threaded CPU performance has increased, it's actually done so at a much slower rate compared to GPU computing performance, which actually seems to be doubling, approximately doubling every year. So despite the improvements in memory bandwidth increases, they've not really fully matched the pace of these processing power demands, particularly of the GPUs. And this compounds the issue of creating what we call a memory wall effect. So effectively, if you have the single point of coherency in the DRAM, and every time you have to go out to fetch data from DRAM to actually share between the CPU and the GPU, you're talking anywhere between 140 CPU cycles that you actually just lose in terms of processing just to fetch data in. We want a smarter way of doing this. We want a smarter way of overcoming the memory wall effect. And what we can do is we can actually have on-chip cache, and this drastically reduces the access time of the data. And this on-chip cache, as the CPU tasks get offloaded onto the GPU, they need a way of sharing or basically bringing that point of coherency from the DRAM and bringing it and putting it on the chip inside a cache. So the CPU and the GPU can tightly operate together and hence save power and increase and boost performance and not have to keep going out in a very slow fashion to fetch external memory. So what we need is something to manage these caches, something to actually say to be transparent to the software and to actually understand when a GPU is writing data to the cache, when the CPU is writing data to the cache, to make sure that the integrity of the cache is kept up to date and that both CPU and GPU can access this shared memory without stepping on each other's toes seamlessly and in a very performant way. So we actually provide this in our cache coherency solution from Arteris.
And you brought up two really important points, one of which is that not everything that goes into a heterogeneous design is progressing at the same rate. You've
Yep.
got all these different development cycles, and they're not in sync. And the second thing is that you're adding more features. Each one of those requires different partitioning, different amount of attention from all the resources within a device, right?
Absolutely. Let me show you. So what we have here is we have the Ncore cache coherent controller NOC shown in blue on the chip diagram. And this is connecting the compute engine and coherent ports on the neural processor accelerators we have here. And Ncore is working in concert with different configurations of flex NOC and non-coherent NOC for interconnecting the parts of the system where coherency is not required. So this segmentation enables our customers to design more specialized high performance computing solutions, catering to the specific needs of different data processing components within a system on chip.
Andy, when would you use a non-coherent IP versus a coherent IP? What's the difference there?
Certainly with a non-coherent piece of IP, its primary task may be to offload or to DMA data from one memory to another, or offload data from chip to DRAM. It might be an IO processor that's actually reading in or streaming in data, say from a network interface or a serial port. So in these instances, all you want to do is get the minimum latency possible and the maximum bandwidth. And there's no need really to share caches or basically to talk between CPU or other components. You just tell the components themselves to get on with the task, and the non-coherent interconnect basically gives you a wide data path and a low latency connection to move that data as quickly as possible. In the case where you do need coherency, say for the CPU offloading compute onto the GPU or the neural processor, as we have in our diagram, this is where you want to have shared memory and shared caches. And these caches just need to be managed through hardware. So this is where the coherent interconnect comes in. And that contrasts very nicely with the non-coherent interconnect. Parts of the system will be coherent, other parts of the system will be non-coherent. And these two actually work together very nicely to coordinate all of the data flow around the chip.
And so when you're looking at a coherent system, you're looking at something like AI, for example, where you have lots of Mac operations operating in parallel, right?
Yeah, absolutely. So you might have a number of different clusters, for example, CPU clusters that are working together. You might have 4 CPUs per cluster. They'll be perhaps working in, if you talk about automotive, one will be working in a lockstep mode, one won't be working in a lockstep mode, but they still will be working on the same data or sharing the same cache information. These will be talking perhaps to other processing elements or offloading to a GPU. So really what we have is a system here where everything is actually in concert together working on effectively the same data set, but that data set is being efficiently optimized and the data moved in an integral way around the system.
So from a design standpoint, you're really mixing two very different worlds, right? You're mixing a single source of data, which may be your video coming into a car so that you know that you're going to respond in real time. And then you've also got all this processing that needs to be done on something else, and that has to be done in multiple different levels, potentially multiple different chips, and all that needs to be brought together into some cohesive whole.
Yeah, absolutely. The source data will start off the chip. It will be moved into DRAM. It will be partitioned off for processing to processing elements on the system that may be coherent. That data will end up back in the DRAM. That data may be moved to other parts of the system like a display, and that's streamed non-coherently then to the display, while the coherent system is then again in parallel taking on more data, doing more processing.
What's
Okay.
driving all this? What's changing out in the designs that we didn't see in the past?
So looking at the macro trends for a moment, with the explosion of AI and ML technologies and large language models driving the need for more advanced and capable system IPs, electrification, energy efficiency, green tech, and sustainability on a global scale is driving more energy efficient design functionality of these system IPs. We've got regionalized and government investments increasing geopolitical factors leading to more localized and region specific demands. So if we look at the industry trends that go alongside these, advanced node semiconductor manufacturing is predicting a significant market growth, requiring IP blocks to be able to meet the demands of advanced manufacturing processes. And as chips grow in size and complexity, NOC IP has to scale to manage increased interconnectivity and data flow. Rising costs and scarcity of skilled talent in SOC development are significant challenges, necessitating more efficient and cost-effective IP solutions. And finally, on design trends, NOCs are becoming increasingly complex. They have to meet the demands of the macro and industry trends. So the need for more automation in SOC connectivity is driving the demand for smarter NOCs. Modular designs are trending towards using multi-die and chiplets to enhance performance, scalability, and yields.
One of the challenges that you're facing here is that all these new designs, we're starting to get into much more customization too, right? So in the past, you could pretty much put things down. You said, okay, this is the way it's going to play out for a billion units. We know this is going to work across all mobile devices, for example. Now, what you're getting into is much shorter runs of chips, and they're much more customized for specific uses. Now you have to be very flexible in this coherency, right?
Yeah, you'll get more specific applications, you'll get more complex designs actually, and the scarcity of design as you're actually digging into the technology. So really what you need is automation in this space. So you've got all these macro trends, the industry trends coming along, the design trends coming along. And you really have to find a solution to get yourself to market as efficiently as possible. And as the complexity is only going up, the time you have to develop and to validate these solutions is really pressured.
How complex does this actually get?
Let me show you a fantastic example. This graph emphasizes the shift from traditional scaling of silicon power, frequency, and overall performance, marked by what we call the power wall and memory walls, towards new paradigms like multi-core CPUs, GPUs, IP reuse, deep learning, and large-scale multi-die systems where Moore's law gives way to multi-core chiplets on substrate. So this evolution reflects the industry's response to physical limitations and the shift towards complex integrated solutions that combine multiple technologies and IPs to meet this ever increasing demand for performance, efficiency, functionality in modern electronics. So this really underscores the critical role of advanced system IPs and not technologies in enabling this next generation of electronic devices.
Well, you think about a car and it's getting incredibly complex. You've got all these different sensors all over the place. You've got a zonal architecture, you've got ECUs and some really basic chips. What happens in a vehicle now and going forward as we start getting more and more intelligence into that vehicle?
So if we look into the automotive segment then, where we are focusing today, we can see the automotive segment has a number of domains in this space, each with their respective complexities in terms of network on chip architecture, coherence, and system integration. So as we move from left to right on this diagram, we cover auto MCUs through zonal controllers, vision, into the cockpit, and then out to the advanced driver assistance systems, each having a blend of NoC architectures enabling these advancements, much like we discussed in our connectivity fabric slides above.
And as you start moving further to the right of the slide, you're adding more and more decisions that have to be made in real time, right? So now you're not just taking that data that's coming in from your sensors, you're analyzing it and reacting to it at a ridiculously fast rate.
This need for reduced latency obviously puts a burden on the compute resources and the compute power of the system. So it really has to react in real time, from an event that just needs servicing in an arbitrary amount of time to something that really is quite mission critical. As we said, as we go to the right, where we're coming to advanced driver assistance systems, the reactivity just really needs to be spot on, and there's no lag in the system for obvious safety reasons.
Does that coherency also build in an element of redundancy as well? Because now you potentially, particularly with ADAS, you have to have some sort of safe failover, right?
Yeah, basically what we provide is a level of what we call duplication in the logic. So this actually provides a safety buffer, if you like, or failover. We have ECC and parity checking, basically connecting the data and even actually checking the configuration, fundamental configuration of how the interconnect is put together, as well as the data traveling through it. And all this basically connects through to a fault controller, so that any issue with the system, we can actually safely flag it and identify it straight away, and the system can then move into a safe state.
What does a knock architecture look like in a case like this?
Okay, let me show you. So let's open the lid a little bit on a NOC design, and let's show you what our customers are actually asking for, what a coherent NOC actually needs. The first thing it needs, the ability to support many different protocols. So there are coherent domains where you've got the processor clusters and the coherent GPUs. So these talk protocols such as Chi-B, Chi-E, and ACE. In terms of the I/O coherent domains, these talk AXI or AXI or ACE Lite. So really what we need is the ability to support I/O coherent and also a connection to the non-coherent domains in the system. So we talked about non-coherent NOC earlier. This really is the entry point, if you like, into the coherent domain and the management of that shared data. There's a lot of complex I/O that goes through the NOC as well. That needs to be handled. And of course, the important point here is the memory and the caches themselves. So what we use is a number of internal caches. Those arrange and manage the IO device data coming in. We coordinate that with the CPU data coming in from its own caches. And we actually make that really efficient. Our take is basically making that efficient, having a directory of where all this data is stored. So you can snoop into the different caches of the various parts of the system and actually very efficiently identify where that data is coming from, or whether that data is invalid or needs flushing or refreshing from the DRAM.
And in the past, this was done pretty much in a really brute force approach, right? Sort of a macro level. Now, what you're doing is fine tuning this, saying, okay, not everything needs to be speeded up. Here's what does need to be speeded up. Here's how you do it most efficiently. And it's all about getting that data processed and moved wherever it needs to go.
Absolutely. I mean, the key point here is efficiency. We're talking about the point of coherency, moving on chip. It needs to actually be focused and the data efficiently moved and shared between the devices that need to move and share it. And every time a device accesses a cache, that can be filtered. So every single access doesn't need to be communicated to the device, each individual device itself. It can actually be filtered out, and the device only needs to get the transactions it's really interested in.
This works really well with chiplets too, right? Because now you can say, oh, we can just plug in a chiplet and we can know how to move that data around.
Yeah, we can have effectively a coherent knock on one side of the chiplet and a serial pipe going across, talking to a knock on the other side of the chiplet. And that data is actually transmitted as if the knocks are right next to each other. And the integrity of the data can still be maintained by all the mechanisms that you have on either side of the knock.
And that doesn't matter whether it's sitting side by side or going up into a 3D IC or a 2.5D configuration, right?
Exactly. Yeah.
If you're a design engineer, what do you have to think about in terms of building this? How does it all go together?
So one of the key features of a coherent knock is it has to have a logical interface flow to accelerate the design efficiency. So the flow has to start at architect level with the chip specification and system assembly configuration options. Then it goes into an architectural design phase. Then there's automatic mapping of the knock library elements, and then the optimization and refinement of those elements before the final RTL gets exported. Now, if you do this from scratch, if you have a DIY approach to this, it's incredibly difficult without an automated stepwise flow to actually manage change as all of the requirements come in, as, for example, the design progresses and the designer said, oh, can we add an interface? Can we remove an interface? Can we have a different user bits? Can we change the QoS scheme? Oh, we've just changed the address map. This is causing significant churn to a DIY, if you like, unstructured manual approach. So the fact that we have a stepwise assembly flow is absolutely imperative. Again, entering the configuration, looking at the architecture, doing the mapping and generating the RTL. If we actually stick to that approach, then all of these changes as they come in, all we do is we basically step back in the flow or forward in the flow and make the changes appropriately at the right time and the right place.
And when you think about IP that's supposed to be buy once, play anywhere, that's a little bit different for other IP, right? Because really what you're doing here is buy once and then really hone it into exactly what you're trying to do here.
Absolutely. So what you have here is the need for a configurable knock. It's not a one size fits all solution. It really does need to be refined and configured to get the efficiency out of it and hit the point of the PPA triangle that you want to try and map. Is it aiming for outright performance in this application? Is it really cost effective and it wants to minimize area at the cost of performance? And as you stretch, this triangle for particular applications, you need that flexibility of being able to configure and change and rewind and replay configurations without having to rip everything up and restart.
Where do problems typically come in here? What do design engineers really need to think about when they're putting this together?
Yeah, so floor plan is absolutely key to, of course, the layout team. Every time that interfaces with large numbers of wires are added or removed, or the locations are changed, and memory resizes, the blockages in the layout actually change size, the amount of free space that you have to flow your interconnect wires through changes. And this is causing real headaches unless you have some concept of understanding of floor plan when you design your knock. It can easily be reconfigured or respun as these blockages, the size of the area on die changes as the design changes.
So, Andy, obviously, this has been done in a lot of different places. What have you learned in terms of working with other companies, and what sort of commonalities are you starting to see across all of these?
Of course, we work across different application spaces. We work in the automotive space that we've talked about. We work in the consumer space. We work in the enterprise space. Certain market segments have their own particular requirements. So one thing in the AI space, in the consumer space, for example, is that customers are looking for more mesh-based topologies, more regular topologies. So we have to basically enhance the configuration of the NOT to deal with meshes. Other applications have high bandwidth requirements and low latency requirements, like the automotive space that we looked at previously. That topology might require more of a crossbar style connectivity where you really got point-to-point connections that go through with minimum latency and maximum throughput. So we really have to have a system that partners can actually pull the design together quickly, an environment where they can do testing on different topologies, different configurations, and actually really size the NOT design to really where they need to get to with their application space. So this lends itself to a flexible library of components you can pull together, a flexible flow that you have in terms of designing your knock, and of course the ability to run tests on the architecture you put together to see whether it's performing in the way that you want it to.
And this is part of this whole trend about everything's getting more complex. Now we need a way to manage it.
Absolutely. So really what we have is this database of components. We have the database of the configurations from the customer. So what they're doing is that they're basically just having to change their requirements. And we're then helping them to generate from this vast array of configurable components something that's really optimal for them. They don't have to worry about managing that complexity. It's auto-generated for them. They just have to focus on what are my bandwidth requirements, what's my connectivity, how are the caches set up, what hints do I need to provide to them, and then basically run those tests through the modeling environment we generate and actually see whether the design is actually going to function the way they want it to before they generate the RTL and before they go too far down the flow.
And Andy Nightingale, thanks for a great explanation.
My pleasure, Ed.